Good morning, good afternoon, good evening, everyone. My name is Michaela Blott, and I'm a distinguished engineer with Xilinx Research. I'll talk to you today about balancing hardware flexibility, performance, and efficiency for deep learning. The subject is absolutely central to our research, and I'm really looking forward to sharing some very specific results from the context of network intrusion detection systems that illustrate and quantify the achievable trade-offs that you gain from specialization in the hardware architecture, so loss of flexibility, in exchange for increased performance and hardware efficiency. But before we get to the really interesting part, let me begin with 2 minutes worth of background. I work for Xilinx, which is a fabless semiconductor company, about 30 years old and probably most well known for inventing the FPGA. I guess many of you know it already. In Xilinx, I'm heading the European Research Lab based here in Dublin, Ireland. There's roughly speaking about 10 researchers of us, plus a university program, plus a highly active internship program, even during COVID times. The center of our research, it's all about FPGAs in the context of machine learning, whereby we have a really hands-on approach. So we're building full systems, we're doing benchmarking, and we're carrying out architectural exploration as well as algorithmic optimizations. So why has computing architectures for deep learning become such an important research subject? The reasons for this are as follows. So first of all, in the context of deep learning, compute and memory requirements are already large. So just think of your ResNet 50, which requires over 7 billion operations to process a single input, and these requirements continue to grow. According to OpenAI, post-2012, compute has been doubling every 3.4 months, which is pretty crazy. There are a number of reasons behind of this. First of all, the rise of language processing. Think of Alexa, Siri, GPT-3. These models are 10x to 200x larger than ResNet 50, which was already pretty big. Furthermore, we see increased usage of reinforcement learning and neural architecture search, driving these requirements even higher. So overall, the compute requirements in the space are already at the limits where you can go with standard silicon architectures. Second challenge here is that the algorithms are changing, so we see new operators emerging, new layer types, activation functions, and even connectivity is in flux. What this means for compute architectures is that they not only have to be blazingly fast to address the compute requirements, but they also need to provide a high degree of flexibility. The final challenge here is that this couldn't come at a worse time for the semiconductor industry, as the companies are challenged to provide the performance scalability. We're hitting manufacturing difficulties of shrinking transistor sizes beyond 5 nanometer, and we're faced with exponentially rising design costs. The result of all of this is that architectural innovation becomes paramount. There are lots of innovative and exciting approaches happening, from Cerebrus wafer scale computing, 3D die stacking, quantum and analog computing. In this talk, though, we'll focus on the perhaps less speculative approaches which leverage specialization in compute architectures to achieve the required performance scalability. We refer to those as deep learning processing units, or DPU for short. There are many startups operating in the space, such as Habana, Navana, Sambanova, and GraphCore, to name just a few, but also hyperscalers are building their own custom ASIC for acceleration of AI. Think of Google's TPU, AWS Inferentia, and Huawei's Ascend processor. Even in the automotive space, Tesla is building its own custom AI silicon now. But before we talk about DPUs in more depth, I want to say a few words also about GPUs, as they really play a major role in the acceleration of machine learning workloads. I actually used to have them listed as a separate category, but GPUs are increasingly specializing their hardware for machine learning workloads themselves, so the lines are really getting blurred here. So let's focus on DPUs now in the rest of the talk. We classify the compute architectures in the space of DPUs by their degree of specialization from left to right, whereby the most specialized devices are the furthest to the right in this chart and the most generic to the left of this chart. So with the increasing specialization, as you would expect, we get improved performance and increased efficiency. We identified here, broadly speaking, 3 categories, but there are no hard boundaries really in between them. In reality, this is really a full spectrum. So on the far left, we have the first category, which generalizes DNNs in general. The architecture consists typically of a matrix of processing engines, so we refer to those as MPEs for short. The middle category we call spatial processors. They customize for the specifics of a topology. So here you'd find, for example, an accelerator for ResNet 50 only. And on the far right, we have the extreme variant, where the circuit becomes the neural network. So the topology is actually fully co-designed for the hardware architecture. Let me also say at this point that all of these can be implemented with either ASICs or FPGAs. However, the further you are on the right-hand side of the spectrum, the smaller will be the potential production volume, and as such, FPGAs could potentially make more sense. So you're more likely to use an FPGA with increased degree of specialization. So let me discuss these individual categories now in more detail. And we'll start with the matrix of processing engines first. MPEs are probably the most popular form of specialization of DPU to address the demands of the deep learning space. They look typically something like this, and this is an extremely simplified view of the world. So you have a matrix of processing engines, whereby the individual processing engine could be as simple as a multiply accumulate. It could be a VLIW or even a vector processor. In addition, we have a bit of on-chip buffering, which is necessary for inputs as well as intermediate results. And we have an external memory system with a DMA engine. This architecture is often referred to as layer-by-layer compute, because what you do is you load a batch of input images, then you schedule the compute of the first layer onto the matrix of processing engines, you execute, buffer the intermediate results, and move on to the next layer. So you compute one layer after another. Very important in this concept is the idea of batching. Because assume, for example, your first layer would only keep 4 of the processing engines busy, then your compute utilization would be only 25%. So in order to get a high utilization on your matrix of processing engines, you would actually have to process 4 input images at minimum at the same time. These architectures are customized for machine learning workloads in general in the following way, that the processing engines only support operators that you typically encounter within the machine learning workloads, for example, multiply accumulates, and they're also specialized in the form of ALU types that they support. So for example, tensor matrix and vector ALUs. So let's talk a bit more about what are the implications of batching on throughput and latency. For this, please consider the following chart, whereby the x-axis is latency and the y-axis is throughput. The red line represents measured results from a neural compute stack from Intel executing a multi-layer perceptron. You can see the individual measured data points are over a sequence of batch sizes. The ones furthest to the left is batch size equals 1. Then we have batch size 2, batch size 4, and increasing by powers of 2. What you can see here is that with increasing batch size, I increase my throughput as my device utilization is improving, until eventually I flatten out when I reach a high utilization of my processing engines and I'm getting close to the peak performance of my hardware platform. At the same time, however, my latency increases proportionally to the batch size, as I have to buffer the corresponding amounts of inputs and intermediate results before I can compute the individual layers. So the behavior that you see here is typical for MPEs. And if you're interested, we have many more results like this available for different platforms on our benchmarking website, which is referenced below the chart. Let's move on to the next category now, the spatial processors, or SP for short. SPs, as mentioned before, customize to the specifics of a DNN topology, and they do that in the following way. The hardware architecture actually mimics the topology. So we are creating every layer of a DNN topology inside the hardware, whereby we allocate proportionally compute resources to the compute requirements of a specific layer, such that each layer operates at the same input rate and the flow of the data through this architecture becomes balanced. The inputs are then processed as a stream simply flowing through the SP. Benefits of this architecture are, first of all, increased efficiency. I only instantiate in my hardware exactly what I need in this specific use case. And secondly, I'm getting latency benefits from this, so it's lower latency and no jitter, as I'm avoiding the buffering of the intermediate results in between the layers. So also, to be clear, there is no batching required to achieve a high compute efficiency. The latency is directly correlated with the depth of the pipeline. Another key advantage of spatial architectures is that I can actually scale them to meet the specific computing requirements of individual applications. So let's consider the example of a two-layer DNN for which I create a spatial architecture. As explained before, each layer is represented in the hardware, whereby the allocated compute resources match the requirements in the neural network. Blue shows memory and gray shows the compute elements. Now I can scale the design by, in essence, folding up the hardware architecture, taking parallelism out of each layer proportionally, such that it processes at a fraction of the speed, but remains balanced. The result is that I need much less compute resources. So for example, I could fit this design now into a much smaller device. For example, if I wanted to build a device for IoT application. Here in this example, I went from 100,000 LUTs to 1,000 LUTs, and the corresponding throughput reduced by a factor of 102. So I can also go the other way around and unroll the design to make it more parallel to scale the performance up while I have enough resources in my chip. So if my resources allow it, then I could even scale this to an extent where every neuron in the DNN would actually have dedicated hardware resources, and the result would be that that accelerator could inference at clock speed. So when it's fully unrolled, we talk about a folding factor of 1, whereby the middle one has a folding factor of 10 and the one on the right has a folding factor of 1,000. So again, proportional to the folding factor, I reduce the resources in my footprint and decrease the overall performance. So in summary, spatial processors allow me to scale to meet either performance or resource requirements in the application, and if resources allow, we can completely unfold where each neuron has actually dedicated hardware, and we would create a circuit that could inference at clock speed. Let's now talk about customizing arithmetic, which is one of the most popular forms of optimization used for both MPEs and spatial processors, and very effective to achieve performance scalability. The idea is basically to reduce the data types for both weights and activations as much as possible, while the accuracy loss in my inference engine remains tolerable. So in essence, we're customizing the arithmetic to the minimum precision required by the use case. And there are a number of benefits that come directly from this. The first one is in regards to my compute requirements. So for example, if I reduce my multiply accumulate from operating at 8-bit 8-bit down to 1-bit 1-bit, the hardware footprint associated with that multiply accumulate will shrink roughly by a factor of 70. So if my hardware cost now is smaller, that means I can instantiate 70x more of this operator in the same device. And as CNNs are incredibly parallel, that will directly translate into a 70x speed up. So we've actually benchmarked this for a whole number of different positions, both through RTL and high-level synthesis design entry, which are shown in this chart below. Let's talk about the granularity of customization. So in the context of MPEs, let's say I customize my processing engines to operate with a minimum precision of 8 bits. And as I'm doing a layer by layer compute here, and I really don't know where the compute of each individual layer is going to end up on my matrix of processing engines, This implies that the minimum precision that I can choose for my weights and activations across all of the layers is int 8. In the context of the spatial processors, this is very different because I have dedicated resources for each of the layers. This means I can choose mixed precision between weights and activations and across all of the layers. So in summary, spatial architectures can exploit custom arithmetic at a much greater degree than MPEs can. Another dimension to customization of precision is to optimize over runtime using runtime programmable precision. Let me explain what I mean with this chart here. So on the x-axis, I have this time the execution time, first executing layer 1 on input I0, then layer 2 on input I0 until I'm finished with my first input. Then I process the second input, so I1, and compute layer 1, layer 2, layer 3, and so on. On the y-axis, I'm showing the minimum precision required for the execution of this layer on this specific input. And there you can see that layer 1 for I0 needs only 3-bit, while layer 2 for I0 needs 2-bit, and so on. And this can be different for every input. So if I have a FP32 implementation as shown through the black line, then that area between the blue boxes and the line would be representative of the waste. If I harden my custom arithmetic, say to int 8, then I've significantly reduced the wastage. So this is everything that we've discussed up until this point. But there's further scope, and that's what can be exploited with runtime programmable precision. By the way, this works both for MPEs and SP, but makes most sense for the MPE, of course. One way to build runtime programmable precision is through bitserial architectures. So most common architectures leverage bit parallel implementations as shown in the left example, where you have an ALU and 2 operands feeding into it. In parallel, you clock in the full operand per clock cycle, as is shown in the animation here. With bitserial architecture, this is very different, and some of you might be familiar with it already. Here, I shift my operands in 1 bit at a time. So the result of this is that at runtime, I can then decide how many bits per operand I actually want to process. The key question in this regard is how much hardware overhead does it actually cost to enable this? So we experimented with matrix multiply and FPGAs and found very little difference for smaller precisions, getting specialization without losing generality in the hardware architecture. Thereby, this provides another interesting twist on this whole story between generality and performance. But there's a lot of system complexity associated with it, which shouldn't be neglected. Now let's move to the most extreme variant. So in this category, my topology is fully co-designed for my hardware architecture. In essence, here I'm no longer specializing my hardware for the DNN, but it's actually the other way around. So the circuit becomes the DNN. We refer to this project as LogicNet, and I'll explain you the details in the following slides. The main idea behind LogicNet is that a lookup table in your typical FPGA fabric can be identical to a neuron in a DNN. So any neuron with 6 binary inputs, floating point weights, batch norm, thresholding, activation, and binary output can be mapped one-to-one to a LUT in the FPGA fabric. And by the way, there are ways to scale this to more inputs and higher precision inputs and outputs, but let's keep it simple for now. So with this, we can then turn the whole problem onto its head. So up until now, what we did was we pick a DNN and then we train it, whereby during the training process, we adjust the parameters of the DNN while iterating on the training data set until we achieve the desired accuracy. So then we optimize the hardware for it and deploy it. So with LogicNet, we can do it now the other way around. So we start actually with the circuit and assume that it is an unrolled DNN. So this DNN is naturally sparse to suit the interconnect in the FPGA and the limited fan-in of the lookup table. Then we train this DNN, whereby again during the training process we adjust the parameters of the neural network until we achieve the desired accuracy, whereby this time the parameters that I've adjusted will directly map to lookup table contents. And then we can deploy this, whereby the generated circuit is maximum performance by design and will classify at clock rate. So at this stage, you might wonder, How is this actually different to the fully unrolled spatial processing architecture that we previously discussed? So compared to the fully unrolled spatial processor, this architecture is optimally suited to the hardware. It caters to the sparsity of the interconnect in the device and the limited fan-in of the lookup tables, and thereby achieve even higher performance. So you will see in the result section where we can really go with this. Let's take a look now at a specific example taken from the context of deep network intrusion detection and quantify these trade-offs between flexibility, performance, and efficiency. Let's see what can be really achieved through the discussed forms of specialization. The chosen example is deep network intrusion detection. Here's a block diagram of the system, which consists of a packet processing pipeline with network interfaces on either end, a feature extraction block which feeds into the traffic classification engine. This is of course where the DNN sits, followed by a packet filter which either drops or passes the packets. The performance requirements are as follows. If I were to deploy this in a 400 gigabit per second Ethernet link and I assume a packet size of 64 bytes per packet, this would translate into 600 million requests per second for my traffic classification engine, which is huge. But even at 5G rates, let's assume 20 gigabits per second, we'd be looking at 30 million requests per second. So those are very steep requirements. The application is also latency sensitive, as I have to buffer all the traffic while the decision whether to drop or pass it is pending. So at 400 gigabit per second, if I have only 1 millisecond latency, this already translates into 400 megabit storage space that I need inside my device. So the application is really latency sensitive. So here are the implementations that we considered, all of them, of course, on FPGAs. On the far left, we have an MPE implementation with the original 3-layer MLP, which uses 92,000 ops to process a single input and leverages an 8-bit integer arithmetic. In the middle, we have two spatial processors. One is fully unrolled, so folding factor 1. One is folded up 8 times. The SP architectures run the same MLP as the MPE architecture, with the only difference that it leverages reduced precision with 2-bit data types for wait and activations. And then on the far right, we have the LogicNet implementation. So here the neural network is different. First of all, through the co-design process, it ended up being much smaller. It only uses 15,000 ops to process an input, so about 6x smaller than the MLP on the left. And it is much sparser. So do note the 7 inputs per neuron that we have on the far right-hand side. So those are the 4 implementations with increasing degree of specialization from left to right that we consider in the experimentation. Here are the performance and latency results of these implementations. The MPE implementation, again shown here on the far left, is as expected the lowest in performance, achieving 22,000 requests per second with a compute latency of 26 microseconds. By the way, we excluded all data movement overheads from this measurement. The folded spatial processor clearly shows the speed up through custom arithmetic, scaling performance by a full 3 orders of magnitude to 25 million requests per second, so already getting into the space of the communication requirements. Also, we can see a dramatic latency reduction from microseconds to nanosecond range, which is the result of the spatial data flow implementation, which inherently reduces buffering between layers, if you recall. So only 240 nanoseconds measured latency here. When fully unrolled, so all the way down to a folding factor of 1, we can scale the performance accordingly by a factor of 8 up to 200 million requests per second and reduce the latency further down to 30 nanoseconds. Finally, on the far right, we have the LogicNet implementation, which delivers, as expected, the highest performance overall with 471 million requests per second. So there's another factor of 2x speed up compared to the fully unrolled spatial, and it only has 9 nanosecond latency. So here you can really see the additional benefit from the full co-design. So remember the sparse connectivity simplifies the logic in each neuron, which means less pipeline registers are required, which decreases the latency of the implementation. Also, the sparse connectivity simplifies the routing resources that are needed by the circuit, which allows us to increase the clock frequency. So this design inferences at clock speed, which is 470 megahertz, of course. So overall, the example in network intrusion detection really showcases how the specialization can scale the performance and reduce latency by orders of magnitude. So this is a fantastic benefit, but which is really only possible if your end application is amenable to it. So you have to bear that in mind. So in this case, it allowed us to meet even the requirements that you would encounter in communication infrastructure. Remember, we're looking here at hundreds of millions of inferences per second. Let's take a look now at what expense this performance scalability comes in form of compute costs. So we think of this as a form of hardware resource efficiency. The MPE implementation, again shown on the far left, costs 234,000. The metric is, by the way, a weighted sum of number of lookup tables and DSPs, whereby the DSP gets a weight of 100. Formula is given below the figure. In brackets, we show the normalized compute cost per operation, where we basically divide this formula by the number of ops in the neural network. So let's compare the MPE now with the spatial processor. So first, the Fold-8 spatial processor architecture, to remind you, is running the same MLP as the MPE. And even though it gives us 1000x speed up, it actually only costs us a fraction in hardware resources. The reason behind here is, most importantly, the custom arithmetic. Remember, we're only using 2-bit arithmetic instead of 8 bits here. So also because of this, the normalized cost per operation has naturally decreased. So when we're unfolding this further now, so to a Fold-1 spatial processing architecture, the resource cost scales accordingly up with the increase in additional implemented parallelism in your design. Remember, unfolding increases in speed at the expense of hardware resources. The LogicNet on the far right-hand side has the smallest footprint while achieving the highest performance. Remember, it's another 2x faster than the fully unrolled spatial architecture. So the reduction in resources has a couple of reasons. First of all, to remind you, the LogicNet topology has 6x fewer operations compared to the MLPs. So that will be giving you the first XX, but we actually observe here a factor of 20x. So where does the rest come from? And the reason for this is that the sparsity in the DNN simplified the logic in the circuit, and that's the root cause why we get a factor of 20x decrease in resources. So overall, the results that you see on this slide here show that, in particular, custom arithmetic and learned circuits like LogicNet can greatly improve compute efficiency, even though they give you a massive performance boost. The other important hardware resource cost to consider is memory. And as one expects, reducing precision has a direct impact on memory footprint, but the SP versus MPE story is much more complicated. So for MPE, we need to typically double buffer all intermediate results between layers. Remember, we have a layer by layer compute. But on the other hand, I only need access to weights of one layer on chip at a time because I only compute one layer at a time. For spatial processors, on the other side, I need parallel access to all weights in all layers, which means all weights are ideally on chip. But on the other hand, the activation buffering between layers is minimized, as I only need to buffer just enough data for the compute of the next layer to start. So let's see how this manifests itself in our example. So here we're showing in the chart the calculated memory cost as the total size of memory used. So we get this number from using the number of utilized block RAMs multiplied by the block RAM size. And then we divide this with the required weight footprint for the normalized metric in brackets. So you can see here, when moving from MPE to SP, the memory cost shrinks significantly. And this is mostly down to the customized arithmetic really, which reduces the memory requirements 4x going from int8 to int2. The most interesting part though is what happens when we fully unroll the DNN or we use LogicNets. At the moment where we have dedicated compute resources per neuron, then the weights can be completely absorbed into the logic and the memory cost evaporates. So upshot here is that customized arithmetic and learned circuits can greatly improve memory efficiency. So in summary, the example illustrates the trade-offs between specialization and performance and efficiency. It shows that specialization can be highly effective to scale performance. Think of the custom arithmetic, and reduce latency. Think of the spatial processors by orders of magnitude. Of course, this is only possible if your application is amenable to these forms of optimizations. But they can be effective and can even allow you to meet extreme throughput requirements, as you would see it, for example, in communication infrastructure. Furthermore, the reduced precision and the learned circuits that you have in LogicNet can shrink the compute resource requirements despite the speed up that you're getting from them. And memory resource efficiency improves with specialization. So remember, with unrolling spatial processors and LogicNets, you actually absorb on-chip memory requirements completely into the logic. The challenge in specialization is how can we explore the potential in the various compute architectures, and how do we make the specialization available to a broader spectrum of end users? And that is the aim of our project FIN. With FIN, we want to provide the tools and platforms for the exploration of DNN compute architectures. So firstly, it offers an end-to-end tool flow to make the specialization available to machine learning engineers. So even machine learning engineers can take advantage of the spatial architectures and the custom precisions. Secondly, and perhaps more of interest to this audience, is that it's fully open source. So it provides you with the transparency and the flexibility to explore hardware architectures. I'm sure there are many more innovative options to implement DNNs that we haven't thought of yet. So FIN can provide you with the tools and platforms and infrastructure to make the exploration of architectures easier. So as just mentioned, FIN offers an end-to-end tool flow. Input is a DNN and output is working hardware. It consists of a stack of 3 modular components. First of all, at the top, there's the training library called Brevitas, which provides all algorithmic optimization support. It has specifically strong support for quantization-aware training, and it can even learn the minimum precision to achieve a certain accuracy target. From here, we export the trained model via an annotated ONNX representation. This feeds into the FIN compiler, which is the middle component. FIN compiler generates the specialized hardware accelerators. It can generate the spatial architectures, and it can scale the hardware up and down to meet the performance and resource requirements in your use case. It generates a DNN IP, which is made for easy integration with PINC platforms, but can be embedded into any of your infrastructure designs if you like. We support specifically deployment in both embedded platforms and Alveo platforms, and if you like to experiment, there is freely available infrastructure available in form of the Xilinx academic compute clusters. The status of this project is there's lots available. We've been working on this for a couple of years already, and we have a growing community. So there are many student, hobbyist, and school projects out there that have leveraged FIN. There are university classes on computer architecture being taught with FIN, for example, at Stanford, and there are a number of industrial applications too. The development is still ongoing, so we're currently working on a release of LogicNet. We expect to have this out in the next month or two. We're also working on multi-node deployment, which allows you to run distributed neural network inference, for example, on the Xilinx academic compute cluster. And at this stage, we're really looking to grow the community, to build out a bigger portfolio of differentiating applications, and to broaden the library that holds all the architectural alternatives. So if this is something of interest to you, we'd love to hear from you. With that, we reach already the end of this talk. I hope that this talk, with the example in network intrusion detection, helped to illustrate and quantify that specialization in form of spatial processing, custom arithmetic, and learned circuits, such as LogicNet, can be a highly effective tool to scale performance, reduce latency, and improve resource efficiency for DNN inference. That is, of course, only if the application is amenable to the chosen form of optimization. The degree of specialization limits the target application, of course, unless we use FPGAs, so we lose flexibility. Coming back to the overall theme of the talk, it's always a balancing act. Finally, tools such as Fin can help make architectural exploration a bit easier. If you're interested, please contact us. With that, I would like to conclude the talk. Here is a list of the most important references if you're interested. Thank you very much for your attention.